and welcome back. In this section, we're going to review a cardiac muscle and how it contracts, and we'll go in great detail about this to make sure you understand it. So we need to review first skeletal muscle contraction. And so let's refresh your memory that we are going to have a muscle contraction curve where we're going to have depolarization and repolarization due to influx through voltage-gated sodium channels where sodium's rushing into the cell and potassium channels where potassium's rushing out of the cell. And so the curve looks something like this. From start to end, this entire process takes about 0.4 of a second. So at first we have sodium channels opening and we're going to have a rapid influx of sodium giving us depolarization from the resting membrane potential of about -70 all the way up to about a +30. And then once we have finished our influx of sodium, what we see is the effect of the efflux, the outward flow of potassium. And so then and this is a slower process. And so we will go in a negative direction, and we actually go more negative than our resting membrane potential. We have that process of hyperpolarization occur. And because the potassium channels are a little bit leaky, it will take some time, but we will get back up to our resting membrane potential. As I said, this entire process takes about 0.4 of a second. So that's skeletal muscle, which most of us know pretty well from spending a lot of time on that in physiology. So now let's go and see the differences between that and cardiac muscle. So in cardiac muscle, we are not only talking about sodium and potassium channels, but calcium channels are super important. So way back when I was talking about having ion channels, when we're talking about neurons and things like that, I did mention the calcium channels, but I said they weren't important for us back then, but now, today, they are super important. And so you end up with a curve that looks like this. So let me take you through it. Well, the first thing to notice is the resting membrane potential is totally different in cardiac muscle than it is in skeletal muscle. And in fact, we're at about a -90 for our resting membrane potential. And with that rapid influx of sodium, we will get to about a +20. So there's a larger change in voltage in cardiac muscle than there is in skeletal muscle. And so we have a super rapid depolarization occurring from the sodium. This is going to be followed by calcium channels opening, and these are slow opening calcium channels. So the calcium doesn't all pour in just like all the sodium poured in. Because these are slow, we will have a slower influx of calcium over time, which gives us this flattened plateau. And then after this, we see what happens due to the opening of the voltage-gated potassium channels, where we will have an efflux of potassium. So unlike skeletal muscle, there's 3 parts to the cardiac muscle contraction. The first part is the rapid opening of the sodium channels, giving us a rapid depolarization. The second component is the plateau, which is a prolonged depolarization due to the prolonged opening of the voltage-gated calcium channels. And the third part is the opening of the potassium channels, allowing potassium to exit the cell, causing the repolarization. So if you look at this bottom right picture, you can see each of these ions separately and what's happening to them over time. So initially we have a very rapid sodium influx, giving us a rapid depolarization. This is followed by a slower in red calcium influx, which takes multiple milliseconds to occur. And then in blue, we have the outward flow of potassium. So as opposed to just 2 ions being involved in the skeletal muscle, and yet the entire skeletal muscle contraction taking about 0.4 seconds until the next skeletal muscle contraction can occur. In the heart, we have 3 ions involved, and this is faster. This entire process only takes about 0.3 of a second. So, taking this picture where we can see in green the depolarization due to sodium and calcium, and in red the repolarization due to potassium, we can see that where the refractory period is entirely during the sodium and calcium ion movement, as well as the beginning of the potassium ion movement. And the actual muscle contraction occurs slightly after the beginning of the refractory period and ends slightly before the end of the refractory period. So this plateau increases, our refractory period increases where we're having contraction going on. So it's super important in preventing our cardiac arrhythmias, those irregular heartbeats that occur to some folks. And so when you were thinking about heart muscle contraction, calcium is the biggie. It's regulating this. And as I have written, this entry of these extracellular calcium ions is what's causing the release of calcium from the sarcoplasmic reticulum, and thereby causing high calcium levels in the cytosol. So let's look at that in more detail. So to refresh your memory, on the sarcoplasmic reticulum, we have a receptor known as the ryanodine receptor, which is often abbreviated RYR for ryanodine receptor. And so this is it on the sarcoplasmic reticulum, and what it is doing, it's recognizing whether or not there's calcium on the cytosolic side. Now there is lots of calcium being sequestered inside the cytosol, being stored in there. When calcium levels on the cytosolic side rise, that is going to cause this ryanodine receptor to open a channel so that calcium can be released from the sarcoplasmic reticulum. And this actually has a positive feedback. The more calcium then that is released, then the more this receptor is activated, which gives us even more release. And so we get a very sudden, massive increase in calcium locally in the cytosol. So if you recall, calcium was in the sarcoplasmic reticulum. When we have depolarization of the plasma membrane and calcium entered the cell through those slow or L-type calcium channels, that new calcium in the cell then can travel by diffusion over to the ryanodine receptors on the sarcoplasmic reticulum, which then triggers calcium release from the sarcoplasmic reticulum, giving us a massive increase of local calcium, which is known as a calcium spark. And it's this calcium spark that's going to trigger contraction, as we will see shortly. But before I go through that, I want to talk about what happens after the contraction to all of this calcium in the cytosol. For this, we have something called a circa pump. So circa just stands for sarcoendoplasmic reticulum calcium. Okay, so it's all this calcium. It's calcium that came in through the slow channel calcium receptors, as well as the calcium that came out due to activation of the ryanodine receptors. So now we have this high cytosolic calcium. And what happens to this calcium is we have an ATPase, which will act on ATP, giving us ADP and inorganic phosphate, just like ATPases do. But what this energy is used for is to send calcium back into the sarcoplasmic reticulum. Now, this does not occur at the ryanodine receptor, but it occurs elsewhere. So let's put it all together. We have an action potential in our cardiomyocyte. Now recall, because of intercalated discs, this most likely is coming from an adjacent cell, not coming directly from part of the conduction system. But no matter what, we have this action potential, which is going to work on sodium influx, and then the part we're interested in is the calcium channels are going to open. And so here's the calcium channel. You can see what was blocking the gate. The gate door is now open, and we have this slow but persistent influx of calcium. Calcium diffuses in the cytosol and then binds to the ryanodine receptor on the sarcoplasmic reticulum, allowing calcium to exit. Positive reflex, we get more and more calcium exiting the sarcoplasmic reticulum, and we get this calcium spark. And so all this calcium together then becomes a calcium signal, which works on the which binds to the troponin, and thereby pulling the tropomyosin off the active binding sites on the actin, allowing the myosin heads to go in and ratchet it, causing a contraction. After this, the calcium is kicked off the troponin. It is back in the sarcoplasmic reticulum. We're going to use our circa system with an ATP to send calcium back into the sarcoplasmic reticulum so that we have stored calcium to generate another contraction later on. In addition, some calcium will diffuse back over towards the plasma membrane, and it will exit the cell in exchange for sodium ions. And those sodium ions, which have now entered the cell, are going to be used in a sodium-potassium pump to bring potassium back into the cell where it belongs. And notice during this relaxation phase, that calcium channel is closed, the gate is shut. All right, that's it for this part. I strongly suggest that you pause it and go through this process and talk all the moving parts. Okay. Now, I do want to point out one thing, because we talked about IP3 being a secondary messenger recently when we were talking about the endocrine system and how that caused calcium increases, which that's totally unrelated. Okay. That stuff doesn't involve a ryanodine receptor. So that's done and over with. We're on something totally different now. All right, that's it for this section, and I will see you again. Have a great day, and thank you for all your hard work.